Hi, and welcome to the contrast webinar called What the WAF, all about understanding and augmenting what the web application firewalls cannot see. In this webinar, what I want to do is to go through the context of talking about the architecture of WAFs, why they exist, what purpose they serve, how they function in an overall architecture. Then I want to talk about the differentiation between cloud-native WAFs, which are available in the major cloud providers, and the on-premise WAFs, and figure out where the two unify and where they diverge. And then finally, I want to go through and talk about the architecture of self-defending applications to talk about the ability to augment things that the WAF cannot actually see so that you can get an effective security defense within an application. To introduce myself, my name is Eric Koslow. I'm a member of the Contrast security team focused on talking about self-defending software, figuring out how to work inside of applications and have some actual context. Prior to that, I did a lot in the vein of cloud migrations and data center optimization for various workloads on VMware, different container systems, porting workloads into AWS and Azure, and also dealing a lot with the management of cloud bills in terms of optimizing cost. Prior to that, I was one of the product managers in Oracle for Java 8, back at the time when Java had a significant number of security vulnerabilities with a lot of 0 days coming in and just attacking the platform that a lot of developers use. I had joined the Oracle product management team to help mitigate those security problems, and we moved it from being a period of frequent exploits into having about a 2-year shutout of 0-day vulnerabilities, during which time the Java JRE dropped out of all major cyber risk reports. In addition to that, I'm also a software development course author, so I've published a couple different courses online through Pact Publishing about things like graph analysis, which is used heavily in the static analysis field, talking about cryptography, since I used to run the Oracle Java Root Certificate program, and just different types of data analysis and coding techniques. And with that, I want to get started and talk about the web application firewall, cover the architecture, why they function, and why they need some augmentation. I always like to start analysis by identifying what problem a certain technique or technology solves. And the reason that web application firewalls were created in the first place is due to something called the OSI model that represents how network traffic moves from host to host. And what we find is that layer 7, which is the application layer that has the actual context of the data, is where a lot of the action takes place. This is where the data that goes through to be used by an application actually occurs. And things like host firewalls and network firewalls, they don't exist at that layer 7, they exist a little further down to address the question of, can this communicate, yes or no? So they represent the context of, can this data reach the host? Can the data get on the network? They don't actually look at what the data is. And what we find with a lot of applications, especially web applications, is that the application has all that functionality and the ability to access the assets. It communicates to the database. It uses different files. It's what has the actual information that a lot of the attackers want and that companies don't want to lose. So with everything going over HTTP and HTTPS, the industry needed something that could look at that layer 7 network traffic. Now, the way that web application firewalls tend to function is security in the front, application in the back. So when we look at this diagram and a user goes to access an application, firewalls that they go through. And they can actually be in either order. They go through a web application firewall, which analyzes the layer 7 network traffic, looking at a little bit of the data, and then they go through the host firewall. They generally don't even notice the host firewall. That's more for different network probes and things. And then ultimately that data goes to a particular host. That's the bare metal machine that sits either in data center or in the cloud. And on top of that host exists either a virtual machine or a container like Kubernetes or Docker. And the purpose of that VM or container is really to host the application that has the actual workload and is going to handle that user's request. And the application itself is made up of two things primarily. One is custom code, which is what the people wrote to handle what the application actually does. And then that custom code tends to use a number of libraries in order to enable its functionality so that the developers can reuse a fair amount of code. And it's ultimately this application, that custom code in those libraries, that goes through to access things like the database, talk about the application's files, where it gets its data. And when we use an application, that's what we want to host. So this final item over on the right is the cloud spend, because no one goes through and says, I just want to deploy. And the purpose of the containers and hosts is to operate the application, which is what ultimately consumes the cloud spend. Now, what does this architecture provide? What is it that web application firewalls are able to see due to their position all the way on the left, with security in the front, application in the back? Application firewalls, the web application firewalls, they look at data that goes over the network. So over on the left, we have a screenshot of my browser was searching on Google for the word WAF defense. And what we can see here is that we have access to things like the request URL, the type of method, which was just a GET request. We have access to all of the headers, so what content it accepts, if there's any authorization and bearer tokens. And then down at the bottom, we have the query string parameters, where you can see when you search on Google, it has two of them. One is Q, the other is OQ. And you can see I was just searching for the word WAF defense. But what the web application firewalls cannot see with their level of visibility on the network traffic is anything without SSL termination, because they need to actually terminate SSL in order to be able to read the data. And because they're only looking at on the network, they can't see the way in which that data is actually used. They can only see the information as it moves across the network, not how the application actually uses that data. So what happens is they don't have visibility to the things over on the right that occur in the back, which is what assets the application actually uses. For example, does it use SQL at all? And is a particular request parameter or part of the request body used to control any system commands? Web application firewalls, due to their position in the architecture, don't have access to this. They also can't see the connection between URLs and code. So if there's any particular URL that manages or that is managed by just one point of the code, a web application firewall is not able to tell that you're actually hitting the same thing multiple times. Finally, they're not able to do something called software composition analysis, which is looking at the libraries that an application uses, figuring out which of those have known CVEs, and helping people understand the impact of those CVEs. Because of a web application firewall's position looking at network traffic, there are a lot of things that it can't do after that data goes over the network. Now, where does this web application firewall software run? There's two primary locations where people tend to run their on-premise WAFs. The first is a network appliance, and the second is on a host. And the network appliance is just a single box or something that gets placed on an area of the data center. And the difference between that and a host WAF is that host WAFs tend to go on a VM or, I guess, within a container. And whereas might have one network appliance, you'll have one host WAF per host. And the difference is just how many things they watch. So a network appliance tends to sit in front of many different applications, where you'll have one WAF to many applications. And a host WAF is, generally speaking, just for a particular host to protect the data on that particular host as it goes over to the network to be used by the application. So the difference is essentially one to many, whereas you'll have one network appliance and many different host WAFs, each watching its own application. And one of the difficulties that we run into with this web application firewall right away is the difficulty with APIs and the visibility of what the application actually does. So API stands for Application Programming Interface, and it's how applications actually access their code to execute what they have to do. And the reason that they have a difficulty with this is that the assets, like the files and the databases, are accessed by the code through these APIs. And those APIs are not visible from the network because they take place after the data has actually arrived on the host. So what we have is a visibility problem in terms of how that data is actually used. And certain WAFs are attempting to augment visibility into the APIs by using frameworks such as OpenAPI, But the problem is that OpenAPI is really just a representation of structure. It doesn't actually give any insight as to how that data is actually used within the structure. So any normal application data that comes in, if it's unexpected by the application, then it won't be used. And applications only use data that they expect, and WAFs again have no visibility into this because OpenAPI is just a structural representation. One of the other difficulties is that open and common are different words, so a lot of applications don't even use OpenAPI, even though it is a very nice framework. Instead, they will use things like Google RPC. They'll use a different REST implementation for REST APIs. And there's a number of other interchange formats like protocol buffers, Avro, Thrift, Swagger, which was the parent of OpenAPI. But essentially, there are many different things that applications will use. And mostly, the issue is just that OpenAPI simply describes structure. It doesn't give any context as to how that structure is actually used. So the web application firewall is really not able to see any of the assets that are accessed by code. It can, again, only look at the data. So even though this has the word API in it, it's not actually looking at any of the APIs or giving the WAF any new powers. Now, when we look at web application firewalls, there's basically three types of them that people in the industry use. The first is a traditional WAF that tends to operate inside the data center and sits on that appliance or in each individual host, and it can only see network traffic. Another thing that I've heard about is called a next generation WAF, which was released about 4 or 5 years ago. So in a sense, it should be called a previous generation WAF. But they also operate inside a data center or on a host, or they can go up inside of cloud compute. And it's really just deployed in the same area. And it can still, again, only see the network traffic, but maybe it's a little bit closer than before. It's still network traffic. And the last one that's popped up over the last couple of years is a cloud WAF, which is operated by the individual cloud provider using their knowledge of the perimeter that they operate as a network service for themselves, so they can see information that crosses the border to their cloud, either coming in or going out or going between different cloud services. Now, a Venn diagram, when we look and we compare the first two, of a WAF and a next generation WAF, those two are strikingly similar. And the reason is that they both operate on the network data that comes through. So they essentially see the exact same things, they just might use it a little bit differently. So this is the exact same thing that we had before, where we're looking at the query parameters and just the basic headers, or the layer 7 application traffic that goes through. Ultimately, there's not much difference between a WAF and a next generation WAF, especially given that a next generation WAF came out several years ago and is no longer next generation. It's either present generation or a past generation. But when we look at the Venn diagram to compare and contrast a web application firewall with a self-defending application, we can see that there are actually some differences and some similarities. So right away in the middle, we still have all that network traffic. We have the headers, we have the query strings, we have all that data that goes through the network to the application, and they both share it. The reason is that the WAF is looking at it at a network level and is able to see this from the network, and the application has access to its own data because it's the one that asked for it anyways, so they both have this information. Meanwhile, a web application firewall can be pretty good at operating a content delivery network and offloading different requests from reaching the application server in the first place. So this is a nice level of application defenses for like IP blocking, offloading content that's static and might otherwise take away from compute of the application server. And the self-defending applications over on the right have access to all of the APIs. They can see the types of files. They can see what the application's actually executing. And they have access to the files to know what the application is actually using. They have access to the database queries to know if and when those are actually used, and just full visibility into all assets that the application uses, such as SQL, such as NoSQL, or any other customized capabilities that the application has. And the reason that it has this is that they occur after the data has left the network and is used by the application. So what we get is more insight into what actually goes on. Now, the key difference between next generation or traditional WAF and cloud WAF is that the cloud services are not host based. So the cloud providers operate a web application firewall that can just operate across each of their services, some of which are short lived. And they help monitor the cloud perimeter. So anytime data comes into AWS or Azure or Google Cloud, the cloud provider has access to that perimeter and knows how to defend their services from the various compute. So data that comes in and goes maybe to straight to a service such as RDS, relational database services, DynamoDB, or anything like that, the web application firewall can be operated by the cloud provider and just monitor that network traffic for that layer 7 data. The reason is that the cloud provider controls their perimeter. And with the perimeter, we find almost everyone is unified in the notion that the traditional perimeter is dead. So the traditional perimeter is dead. There's no perimeter anymore. The perimeter is dead. Is the security perimeter dead? And people are the perimeter, which I guess if the perimeter is dead, that's a unique perspective. And now I want to go through and talk about the difference between how cloud WAFs operate and how on-premise WAFs operate, where they're different and where they're similar. Now again, when I go to talk about what purpose a piece of technology solves, I always like to go back to the origins of why this technology exists in the first place. So when we talk about cloud WAFs, I always like to start at the definition of what the cloud actually is. And like NIST published something for security called NIST 800-53, they published another document describing the definition of a cloud in a document called NIST 800-145. And what they describe is also used by AWS and Azure, is that a cloud has 5 essential characteristics: on-demand self-service, broad network access, resource pooling, rapid elasticity, and a measured service. And the reason that each of these matter to security is regarding on-demand self-service, everyone is going to help themselves. They're not going to wait for any human expert to go through, do a scan of their application, or make any kind of tuning. The applications need the ability to help themselves without human intervention. Now, broad network access, the point of being in the cloud is the accessibility to other resources, whether those resources are in the cloud, outside the cloud, across different VLANs, or just about anywhere. The point is that applications and data is able to move freely between services that require them. Now, resource pooling regards the ability to consolidate different resources and have a lot of reuse unless you pay otherwise to get a level of isolation. Rapid elasticity is the ability to burst on capacity, typically horizontally, adding different machines or just powers to handle all the workloads so that items can scale up at cloud scale and essentially never run out of things until they run out of budget. Finally, that goes to measured service, which is that budget because all workloads in the cloud, including security workloads, will cost money. And a lot of these resources will cost money even when they're idle. And that money will come in the form of either reserved capacity or, on occasion, storage in the different storage tier. Now, when we have a web application firewall in the cloud, there's 2 things that we can do. The first is we can use the cloud provider's WAF, such as Azure has a WAF, AWS has a WAF, Cloudflare has a web application firewall. And the benefit of that is that we get all their expertise. They just handle it for us. They take care of the licensing. Alternately, we can go through and we can bring our own WAF. We can take our on-premise WAF and either put it up in the cloud, or we can take advantage of someone else's WAF that operates in the cloud, and maybe we get some level of benefit from unification with on-premise things, but let's take a look at how that operates. Now, when we want to host any workload up in the cloud, we want to look at where these things actually take place. So if I'm going to do something, it has to run somewhere in the cloud. And the most likely place that my workload is going to operate is in a service up in AWS called EC2, which stands for Elastic Compute. Alternately, it may be delivered as a service So you can have things that operate as services, but AWS won't really run them because AWS already operates their own WAF, so they're not really going to help you run something else because that's a service that they already provide. So ultimately, any service that you purchase is going to operate up inside of EC2 AWS Fargate, and you certainly could probably use serverless for this, but a pay-on-consumption tool like Lambda is probably not the best location for an active defense against something like a denial of service attack. Paying on consumption for that is probably not a good idea. Now, the key difference between cloud WAFs and bring your own WAF is that a cloud provider really owns their perimeter. They have all of the services, so they know where those services cross, and they know the difference of all the VLANs, all the VPCs, or just about everything that goes on in the cloud. So they're able to figure out what the best position is for each anything that needs to watch that traffic as it goes through. Now, if I bring my own WAF to the cloud or if I do something else, I'm in a sense competing or augmenting the cloud WAF with another WAF, and that WAF needs to run inside of the cloud provider anyways, so I get this little awkward thing where in order to protect the outside of my cloud from data coming in, I need to run inside the cloud so that the data can go back outside the cloud to come back inside the cloud, and that gets a little awkward as a network architecture diagram, but maybe that can be automated. And the last thing is I'm charged a compute cost based on usage generally for forecasting of demands that need to be hosted. So if I'm going to undergo a distributed denial of service attack, I don't really want to pay that based on usage. And my two choices of handling this is I can either pay somebody to run the WAF for me, that bring my own WAF, in which case they'll have to charge me for a forecasted workload, or I can pay based on the compute use that I actually use. So now a distributed denial of service attack is actually attacking the budget. And I want to look at this notion of budget and just talk a little bit about how workloads are priced in the cloud for EC2. And there's 4 different pricing tiers that you can use. There's an on-demand pricing tier, a spot instance tier, a reserved instance, and a dedicated host. And I want to look at each of these pricing models simply to understand how we're paying for things in the cloud when we go to put a workload in there. And right away, what we find for security is that 2 of these are not really a good fit. On-demand and spot instances are not the best fit for security workloads. And the reason is isolated for applications that are short-term, spiky, and unpredictable. Maybe a distributed denial of service attack is an unpredictable workload, but my security monitoring should not be short-term. And spot instances are essentially where someone wants to purchase spare compute from EC2. So when they have lower demand, what they do in order to increase the demand is Amazon will lower the price of what they charge for compute workloads. So if you have an application where it doesn't really matter when the time starts or ends, you just need it to operate and just take care of that whenever you want, that's what a spot instance is good for. But again, a security workload probably doesn't have a flexible start and end time because security needs to be continuous across everything. So right away, 2 of these purchase plans for EC2 are out for a dedicated security monitoring system. Now, reserved instances and dedicated hosts are a little bit closer for a bring my own WAF, but what happens here is that I'm effectively pre-purchasing a reserved capacity that's separate from my applications. So obviously, if I'm going to reserve an instance, I need to know what that instance size is. And that's how these reserved instances are priced, is based on size. And if you look at that item down on the bottom, you're essentially making a 1 to 3 year commitment with your reserved instance. Now, with dedicated hosts, you can purchase it on more of an hourly basis. But the difference is with these, you have to go through and you actually have to know about how much your workload is. And so now we're in a difficulty of figuring out what capacity we need for the workload in order to handle security. And because that's different from the application, it's kind of difficult to figure out how much you actually need. So what happens is you either have to buy significantly more or you buy less. And if you buy more, you're paying a lot more. And if you buy less, then your WAF is going to fall down for a denial of service attack, which kind of defeats the purpose of it. Now, the common cloud access patterns that people use when they want to engage the cloud is one of two things. Either they'll go straight to the service, like maybe they only use one or two, and the application will just go straight to what it needs and just sort of bypass everything and communicate only to what it does based on the application team using particular APIs directly. The other pattern over on the right is a lot of applications will use what's called an API gateway, in which case there's a single unified entry to an application or the cloud entry point where they can go through and the applications can reach their actual workloads. And this is a nice proxy enabling everyone to use different services. Like it gets to hide from the client what is a Lambda, what is an endpoint on EC2 with a custom compute workload, any type of service, and it just provides a nice single unified location into the cloud. Now, when we look at this gateway with a custom web application firewall, it gets really complicated. So this is literally a diagram that I found of how can I deploy a WAF into the cloud. This is a literal diagram. I didn't make this up. I didn't hunt for it. And what I find confusing about this diagram is a lot of things, but predominantly that it actually shows a lot less than the other application gateway diagram. So here, our different AWS services are not even listed. It doesn't show AWS Lambda for serverless. It doesn't show me S3. It doesn't show me RDS for relational data services. And it doesn't show me any of the actual services that my application is actually going to be used that are theoretically protected here. Instead, it shows a whole lot of complicated things that might be necessary but should really be handled automatically. So we have a VPC here, a virtual private cloud, and then we have a couple other things like we have an auto scaling group, which auto scaling in the cloud as a measured service means auto scaling on money too. Which auto scaling your budget, okay. Then we have a couple different subnets. So this one has 4 different subnets in here. It has an external load balancer, which seems to operate in the cloud, so we need that too. There's a NAT gateway in there for some reason, which seems to make its way over into AWS CloudFront. We have a management server in here, and we have a lot of different arrows in different colors crossing each other and going different ways, and just being, generally speaking, very confusing. Another technique of this is maybe we can go through and just do something like making a simple DNS change to get a WAF and routing everything through one particular location. So does changing a DNS entry make a cloud WAF? Anytime the headline is a question, the answer is typically no, in which case it isn't. And the reason is that the AWS WAF is already operating right here with Amazon CloudFront. It's called CloudFront because it's the front of the cloud, and a web application firewall is security in the front, application in the back. And the thing is, when we go to have our own custom WAF here, it has to run somewhere, which is generally going to be in EC2. So the DNS changed WAF is going to run in that EC2 area anyways, and you don't avoid using CloudFront, which already has a WAF. So what happens is if we just go through and change DNS in order to engage a WAF because it's easy, then basically what we've ended up with is the context of a double WAF. They're both 2 different WAFs. I have to go through them both anyways. Maybe I just don't turn one of them on. But I've essentially accomplished nothing new, or I've gotten no new visibility because they both look at the same network traffic. Now, this is the actual architecture diagram. This is the official architecture diagram of the AWS WAF. And you notice there's CloudFront again. So you're already using AWS CloudFront. And when you have this kind of double WAF, like if you replaced AWS WAF with another one, they're both looking at the same data. So if I want to augment a WAF or if I want to instill a protection, then what I want to focus on is things that the web application firewall cannot see. For example, what happens behind CloudFront? If we look over at AWS, it talks about item C as SQL injection. And the big question is, because SQL is accessed after the WAF happens, how does the WAF actually know that SQL is even used? Now, a sensible WAF augmentation would be just letting the cloud provider manage the CDN, which takes place in CloudFront anyways, which is why AWS puts their WAF there. So in this case, I would let the cloud provider manage all of the network diagrams that were from that complicated diagram earlier. So let them handle the VPCs, the virtual private clouds. Let the cloud provider handle all the subnets, all the services, any kind of inter-service triggers that go on between the AWS services. And I would focus on looking beyond the front door. And the reason is that if I'm going to differentiate my business through my application, then I should focus on securing that application, not creating a different AWS topology that AWS already creates and competing with them in their own environment. So why would I secure my application instead of just securing it in the front? Well, a couple reasons for this is one, when security is part of the application, you can't go around it, such as reaching the application through its actual DNS entry. Also, when security is part of the application, I can still purchase capacity because I'm just purchasing capacity for the application. So all four of those AWS EC2 pricing workloads come back because it's now part of the original workload. And when security is part of the application, you don't change any of its diagrams. So there's no notion of creating different subnets or VLANs or VPCs. The diagram is exactly the same because the application goes where it goes already, and security is just part of the application. And how does Contrast go through to actually support these self-defending applications? Well, we have two capabilities for this. The first is called a language agent, and the second is called a proxy agent. And what language agents do is they go directly inside the runtimes to help make each runtime self-defending and know what to look at. So it has full visibility into the custom code. It can see the libraries, the frameworks, the app server. And the reason that they have a high level of accuracy is because of their location, they can see how that data is actually used. So rather than just looking at the data going over the network, they're watching how that data is actually used by an application to figure out which threats are actually relevant. Now, the proxy agent is used for cases where there is no language agent. So it's effectively a language agnostic next generation WAF or traditional generation WAF that operates with any other languages. So things like C and C++, if you have a web service that's written in those, if you have something in Rust, maybe Go, or just about any other language, the proxy agent still has the same level of visibility into network traffic, just the same as any other web application firewall. However, the proxy agent, like a WAF, cannot see inside the application like a language agent can to gain that additional context. Now I want to go through and talk about why we'll augment the WAFs with these self-defending applications, and specifically what these self-defending applications gain for application security teams and developers. I really like the way that Microsoft Azure talks about their web application firewall, where they call it part of the front door service. And with AWS calling it CloudFront and Azure calling it a front door service, this is again, each web application firewall for the cloud is referring to this as a defense in the front. So what happens is they watch the data that goes over the network and they're able to look at that traffic. But a key question here for application teams is, what about the inside of the cloud? What about the way in which this data is actually used? And a key point here of what you want to get is an example right here. Let's assume that there's a SQL injection attack that somebody is actually instituting, and they send this data, this apostrophe or 1 = 1, which is a valid SQL injection attack. You can look at that at a network level and you can say, this looks like a SQL query, because a lot of application firewalls literally look for the signature of 1 = 1. The key question, though, is how does a web application firewall even know that SQL is being used? So we have a popular NoSQL database called MongoDB that has grown significantly and is even a publicly traded company that doesn't even use a SQL syntax. So MongoDB is a wildly popular database. AWS has something else called DynamoDB, or they have something else that uses Mongo syntax. And what we find is that maybe we can look and we can say, here's a valid SQL injection, but if SQL isn't being used at all, what is the point in continually looking for SQL injections? Then the issue is that a web application firewall has no way of knowing if SQL is actually used. So right here is an example that they can't differentiate between an attack and a vulnerability. And the problem with this is the level of noise that it creates and an inability for anyone to actually investigate issues. So let's say that SQL injection attack comes in, and instead of going to a database, it doesn't actually reach a database. Let's pretend it's accessing a file. Now you're trying to go through and access a file with a SQL injection attack, which is weird, but it doesn't actually harm a database because no database is actually used. A web application firewall, without having this context, is going to continually go through and constantly alert people to have to investigate noise. You better tell somebody that we're being attacked right now and you need to investigate what this attack is because our web application firewall is seeing it. But the problem is, this attack can't actually work, so it might be nice to know that somebody's attacking us, but if the attack is not relevant, it doesn't really matter. What I care about is the ability to block attacks that are actually effective and investigate things that actually matter. I don't need to hear all of this noise about attacks that are reaching things that are never even vulnerable to those attacks. And the way that Contrast solves this problem is by going inside of applications to see what's actually happening. So in the way of Java, we use something called instrumentation, which was introduced back in JDK 1.5 in about 2004, and is fully compatible with the way that Java operates. Like this package is literally java.lang.instrument, so it's part of the language itself. The runtime is specifically designed to enable this type of instrumentation that Contrast is doing. And the performance is quite good, and the reason is that because instrumentation becomes part of the application, all of the optimizations through the normal just-in-time compilation happen, and the security is now optimized along with the application, which this optimization is why the JRE is called hotspot in the first place. And it's very easy to manage these self-defending applications because you don't need to go through and change the code to enable it. All you need to do to turn this capability on is to just provide either a new command line argument when you start the application, or you use an environment variable, and all of a sudden the application spins up and the managed runtime takes care of managing itself. Now, this level of context really helps the other systems that people need to integrate with. So if you're going to automatically put vulnerability information into a system like Jira, you want to make sure that that information is relevant and accurate. You don't want to put a whole bunch of attack data into Jira because there's no point in actually investigating it when 99% of it is wrong. So Contrast, by having the insight to understand what's actually happening into applications, you can get effective information in front of the right people, whether they're development, whether they're security, whether they're operations, or how people operate wherever, so that you can have contextual information going to Jira when it matters. You can pass the right information into Slack so that people know about a relevant attack that's occurring. And on the operations side, if you have something like Splunk or ArcSight or any of the SIMs, you don't want to just put generic attack data in there with no context. You might want to be able to put that attack data in there, but you want to be able to differentiate which attacks might actually work and which attacks are just attacking things that are irrelevant, such as SQL injection attacks against applications that don't use SQL. And when you prune down this level of noise using the context, what happens is the people who go through to investigate any types of security issues that happen actually have their time back to investigate things that actually matter. Now, web application firewalls don't also engage the development team, whereas Contrast does. So when you integrate security testing and you have the application self-defending, security tests can be done any place that other tests occur. So as people code, merge, and do their continuous integration tests, Contrast, because it's part of the application, can continually go through and assess these applications to help find vulnerabilities. Now, when people go to release it, you don't want to release it with a whole bunch of known vulnerabilities. Maybe you don't want to remediate them now, or you don't have time to. You can use something like Contrast Protect, so a self-defending application is the remediation. So when you deploy an application, you don't just want to leave security unmonitored. WAF that has no context of how the application's actually using its data. You want something that continually monitors the application and gives continuous visibility, rather than if you only operated on the code and build cycle, what you would get is a strobe light level of visibility whereby you know the security posture maybe every 2 weeks or whenever you do a build, but when it comes time to actually run it, the other 364 days of the year, you don't know what the posture is. So by monitoring both in development and in production as the application operates, security becomes continuous rather than periodic strobe light single-time events. Now, what defenses can a web application firewall actually do rather well? Well, it's like the way that Azure talks about it as a front door service, or the way that AWS talks about it as CloudFront. A web application firewall can do pretty well with the context of SSL management and algorithms because they need to decrypt the SSL anyways in order to analyze the data. They can also be an effective content delivery network, which is what CloudFront does, where they go through and offload requests from the application server that don't need to get there. So if there's something like a denial of service that's coming in and can be recognized by IP, that's a good capability to give to CloudFront or any WAF that's sitting on your on-premise data center that can look at that IP-based information and take the load off of the application server that actually runs the application. And they can also remove possible attacks. So if you just don't want anybody using SQL injection attacks against an application that doesn't use SQL, certainly a WAF can remove those attacks. But because it lacks the context of what the application actually does, they can't differentiate between an attack and a vulnerability. So they're going to constantly alert people about the wrong thing, or just remove a bunch of attacks that don't really matter and would accomplish nothing. What defenses do web application firewalls not do particularly well regarding attacks? Well, one example of these is deserialization, which is a very common architecture pattern for things like the Java platform, different areas in .NET and JSON. And the reason is that web application firewalls don't have the context to understand what's actually being deserialized. So for example, because they're sitting on the network, they don't know if it's actually a Java application or a .NET application that's being used behind the scenes. And in theory, to look at layer 7 traffic, they shouldn't care. But what happens is, for this particular vulnerability class, they don't actually have insight into what data is actually being deserialized. But let's assume for a moment that a web application firewall could block deserialization, and maybe they're going to monitor for that and they can spot it and they'll just block serialization attacks. The issue is that serialization and deserialization is so common inside of things like Java that it's down all the way inside of the java.base system of the JDK9 modularity system. So if you go and start blocking deserialization from the outside, where you can't distinguish what's normal behavior and what's not, what happens is you're going to have a significant level of compatibility on each application, or you won't know when you'll have that level of compatibility impact. So now you're going to go through and just do something weird in the application and create unexpected behavior. However, if you're a part of the application, you have full context as to all the code that's being executed, what's happening in that deserialization process, so you have the right insight to be able to differentiate between safe and normal serialization, which is common, and unsafe deserialization, which is problematic. Web application firewalls also can't do something called software composition analysis, which is to look at software libraries and figure out which of them actually contain CVEs. However, if you're part of the application, you can go through and look at what that application actually uses. So in this example, we have a couple different libraries that are used by the WebGoat application, and Contrast is able to not only see what those libraries and if they have CVEs, but we can also see how many used classes are actually used by each of these libraries. So if we look at the one on the bottom, that xstream147.jar, what we can see is that there's two CVEs, and if we want to upgrade this, we can certainly go from version 1.4.7 to version 1.4.11. However, the used out of total classes, we're using 0 classes from Xstream, which means that while there are two CVEs in that library, we're not actually using that library, so we're not going to be hit by those CVEs because that code is never actually called. Now, these secured applications, they can also scale directly with the workload's pricing. So whereas we talked about web application firewalls before and an inability to forecast demand, when security is part of the application, you're really just back to buying compute workloads for that actual application. So when security is part of that dedicated workload, it's part of the application, so you just choose the pricing model that the application needs anyways. And security is really just going to scale up or down with that application because the two are the same. So if you have an application that can operate in a spot instance with that flexible start and end time, then you just go and you purchase the spot instance for that application. And because security is part of the application, then security just operates inside that spot instance. Now, the performance impact, you don't need to go and increase any of your reservations here, whether you're buying a reserved host or how much you purchase in a spot instance. And the reason is security is part of the application. It just gets to reuse all the data that the application already has. So we're not sending anything back and forth to a central controller. Security is just part of the application, so you're really just reusing the stuff that's already there. Now, when you have this on-premise or cloud workloads, one of the things that we want is continuity or the ability to defend things in a very similar manner. So when we have a cloud WAF like AWS CloudFront or the Azure Front Door service, we can just go ahead and use that as an entry point into the cloud, and we can use these self-defending applications deployed behind the WAF to actually see and gain the context as to which types of security issues are actually going to work, differentiating between an attack and a vulnerability. In an on-premise area, we can use the contrast proxy agent to be that WAF, and then we can use the language agents in order to see behind that hallway. So what we get is a unified approach whereby in the cloud, we use the cloud provider's WAF, and on-premise, we use the contrast proxy agent as the WAF. And with that, I want to just open this up to some Q&A. And we covered so far the way that WAFs are able to support the application network layer, how the difference between web application firewall operated by a cloud provider who owns the perimeter versus bring your own WAF, and how the way in which a self-defending application is different, gaining access to more information that web application firewalls cannot see. And I think what I'm going to do now is to just look at a different screen over here and see a couple of the questions that have come in. All right, so the questions coming in are, WAFs can block SQL injection, so why does it matter that self-defending applications block it as well? Well, WAFs might be able to block SQL injection, but they can only do it based on signatures because they don't know if and when SQL is actually used. So let's pretend for a moment that you could do something with about 100% effectiveness, but you never knew when you were actually supposed to do it. So the only way to retain effectiveness is to do that all the time. So a better way to do this really is to make applications self-defending and focus on things that actually matter based on looking what applications actually do. And if I'm a security person on a security team dealing with attacks, I don't want to constantly be alerted or have to use my time investigating attacks that don't matter. Are you saying we don't need WAFs? No, I'm saying it's your choice whether to use one or not, but rather to use things based on what they're good at. So web application firewalls can see network data, but they don't have any context for how that data is actually used. So that's why they're pretty noisy, or they look for other things unrelated to attacks like volumetric data. The way I see it, better data drives better decisions, and the applications have that data, so let's just go ahead and use it. The next question is, what about languages that Contrast doesn't cover? So Contrast actually covers all languages, either equally or better than a web application firewall alone. The proxy agent is, in a sense, just a web application firewall. So that really matches what everybody knows today. So that's what gives the total language coverage. The language agents themselves are the pieces that actually rely on the language. But those are also what gives the visibility to see the application that is behind the web application to augment what it doesn't see. So between those two, the proxy agent, which is a WAF, and the language agents that see more than a WAF, there really isn't any language that Contrast doesn't cover. And it looks like the last question here. Does Contrast work with things that aren't web applications? So the answer to that is yes. Even though web applications are very popular and have been popular for quite a long time, not all applications are web applications. So the Contrast language agents work inside of the language or managed runtimes itself within the applications that aren't web. So say, for example, you have something like a socket application or something else that just doesn't have a web front end. Contrast is able to hook into those and get some protection against the data that they read from other sources because it's part of the APIs and not just a network defense, but rather it sees what the application actually does. In this case, it would not be web. All right, and it looks like we can wrap up from there. So thank you very much, everyone, for attending. And if you have any questions, feel free to reach out to us any other time. Thank you very much.